Neurons are a lot like electrical wires. In fact, the axons are electrical wires. As you've no doubt noticed, electrical wires are fast. Your brain has to be fast too. If you encounter a slobbering lion, your eyes need to tell your brain to tell your muscles to run. In the neuron, under normal conditions, there is an electrical charge across the cell membrane. The inside has a negative charge and the outside has a positive charge. This happens because of ions, which are atoms that carry a positive or negative charge. There are mostly negative ions inside the cell and mostly positive ions outside the cell. The important ions for the action potentials are sodium and potassium, which are both positively charged. Let's add to the picture calcium and ATP, which will come in handy later. The balloons representing the different ions and the M&Ms representing the ATP. Now let's say something happens. Maybe you step on something sharp. Maybe you see something scary. The point is there is a stimulus, something important that your neurons can respond to. The stimulus sets events in motion. Along the cell membrane, there are gates and pumps, which we will be representing, that react to the electrical current going through the axon. We will now be representing a real-life action potential. The cell membranes are the streamers of the axon, and the balloons are the different ions with the different charges. The spray bottle represents the signal that will be sent at the end of the impulse. Christian represents the sodium gates that allow sodium to go through the cell membrane. I represent the potassium gate that allows potassium to go through the cell membrane. Claudia represents the sodium-potassium pump, which allows these two ions to go through the cell membrane. Gauss basically represents the end of the process that sends a signal to another neuron. You're probably wondering how all these components fit together. Well, that's what we're about to show you. Now the action potential has begun, a moving exchange of ions that runs along the length of the axon. The sodium gates respond. Some of them open and let sodium ions in, so that the inside starts to become less negative. If this reaches a certain level, called the threshold, more sodium gates respond and let more ions in. Then the situation changes. The sodium gates close and the potassium gates open up. The potassium rushes out of the cell, which brings the charge inside the cell back down to where it was, negative on the inside, positive on the outside. Notice, though, that the sodium is now inside the cell and the potassium is outside. That is, they are on the wrong places. So, with the energy from the ATP, the sodium-potassium pumps get back to work and pump the sodium back out and the potassium back in, and things are back to where we started. Now, all this happens at one little segment of the axon at a time. Sodium goes in at section 1, that triggers the potassium to start going out at section 1, and the sodium to start coming in at section 2, that in turn triggers the potassium to go out in section 2, and the sodium to come in at section 3, and so on, like a row of dominoes going down. When the action potential reaches the axon ending, it causes another ion, calcium, to enter the cell, which in turn causes the vessels, the tiny bubbles full of neurotransmitters, to release their contents into the synaptic gap, thus causing the reaction to start again in a separate neuron. Through these processes, signals move through cellular circuits in your nervous system. These circuits transmit, process, and store information such as sensations, thoughts, movements, and reflexes.